if the Lefschetz number of f does not equal 0, then f has a fixed point. How much time do I have left now?
15 minutes.
Oh, really?
Yep.
Oh, wow. I was going to say then, maybe I shouldn't go over the proof. But I hadn't really looked over it in detail. So regardless of time remaining, I still don't want to go over it.
Well, there's still plenty of corollaries and stuff to follow this. So
Yeah.
you got plenty to do. Don't worry.
But it is kind of interesting because it does use some of the things that we used previously with the subdivisions and stuff, and it's kind of an...
So the theorem again is a compact polyhedron, F continuous. If the Lefschetz number is non-zero, then it has a fixed point.
Right.
Man, what does that have to do? Well, I guess
they use here in the proof, it's a proof by contradiction.
I was thinking in terms of the earlier Poincare characteristic. I mean, so if that's analogous to the Lefschetz number, then the other Poincare characteristic of the sphere is 2.
Right, it's not 0.
Not 0, and that's from this perspective why we got those fixed point theorems for the sphere.
Right.
And so this is all generalizing that.
Yep.
Beautiful.
So, corollary.
It's very meshy.
Yes. Lots of meshes. Yeah, even if we don't go over the proof, it is reassuring just to see that that stuff is actually used for something.
Yeah.
Good to know. So, corollary to this. Okay, I guess I should do corollary 9.20 first.
Yeah.
So,
Excellent. Connected compact poly.
path connected. Compact polyhedron. For which h sub n of x is finite. For every n greater than 0, then f from x to x has a fixed point. So rather than characterizing it with this kind of bizarre Lefschetz number, this is an easier characterization to do in practice. Now let's look at the proof here. Let's see, what's the argument?
Basically, if it's finite, that means it's got no free abelian piece, which means it has rank 0, which means the induced maps are 0.
Oh, but then since it's path connected, you get the homology group of... The zeroth homology group is Z.
Right.
And so since everything else is 0, that implies the Lefschetz number is not 0. So the corollary to that (9.21) if n is even, every, I guess, continuous map f from real projective n space to real projective n space has a fixed point. And so proof there looks like we do actually use stuff from chapter 2, at least for this corollary. We saw in Theorem 8.47 that the qth homology group of the nth real projective space is either 0 or z mod 2z for all q greater than 0. So that follows immediately from the corollary. Now, so this next one, Corollary 9.22, if X is a compact, tractable polyhedron, for which, oh no wait, yeah. Then every from X to X continuous has a fixed point. So proof of that, well, contractibility gives us that all homology groups are 0 for n greater than 0. So this is immediate from Corollary 9.20. Of course, as he remarks on the next page, this also implies the Brouwer fixed point theorem, because dn is, of course, contractible. So that's interesting. I mean, I guess we proved that another way too, right?
Yeah. With
When was that? That was back in...
I guess it was the thing. Was that the thing we did early on, and then we supplied the details later?
Yeah.
So it was a combination of like chapter 0 or chapter 1 and chapter 4.
6, I think.
Oh, 6. Okay.
So this is also pretty interesting. I think this will be relevant to what you're talking about, Daniel. It's about topological groups, Corollary 9.23. If X is compact, contractible polyhedron, with more than one point, and there is no multiplication mu from X cross X to X, making X a topological group. So proof. Suppose X were a topological group. Choose Y element of X with Y not equal to 1, which I guess is why we need more than one point. Then phi from X to X defined by phi of X is equal to X times Y, which is equal to mu of XY, is a continuous map, having no fixed points, since Y is not equal to 1. So, since X is compact and contractible, I suppose you can prove that the direct product of X and X is likewise, and therefore that contradicts the Lefschetz fixed point theorem.
Well, phi maps from X to X, you don't even need to worry about X cross X.
Oh, good point. There you go. So, Corollary 9.24. And it's greater than or equal to 1. Then the antipodal map, A from Sn to Sn, has degree -1 to the n plus 1. Didn't we prove this some other way?
Yeah.
I feel like we've proved this before.
Says theorem 6.23. Right. Yeah.
Okay, so they argue.
The argument here
They
is
argue that.
way easier.
Yeah. Trace.
I mean, this is where
AN
the
has to be
algebra
the
and algebraic
three.
topology is finally seen, right? I mean,
Yeah. Lambda of A, by definition, is 1. It's -1 to the n times the degree. This has to be 0, and there you go. And there's that.
so what remains in the chapter is this result on, how to what is a
Right.
what's a tensor?
Yeah, so we know what tensor products are,
Yep.
I hope.
Yeah.
So, the big result here, if you have time to go over this still, the only thing here with tensor products I didn't really know, besides some of the commuting diagram stuff, is this theorem 9.26 essentially says that you can make the tensor product of two homomorphisms.
Oh yeah.
Yeah, so once you have that though, let me see where it is. He talks about universal coefficients for a bit, like I was saying. You can construct homology groups with other coefficients. And he defines that. Defines the nth homology group of x comma a with coefficients g on page 257. A sub h sub n x a g is the kernel and differentiation map tensor product with the identity, the image, the n plus 1th tensor product, the identity. And he says here, the optimistic guess would be that this is isomorphic to just the nth homology group of xa tensor product G. But this is only true for certain G. So the theorem he goes on to show here, let's see, is on page 261, the universal coefficients theorem for homology. And he uses essentially, there's this splitting exact sequence to prove it, but the result you get is that Hn of x, the G is a coefficient group, is isomorphic to Hn of x, tensor product, G direct sum, the torsion, which we haven't defined, but I think you know what that means. So, not as nice as this, but still a relatively easy to comprehend structure. And then I think, finally then, let's see.
The Kunin formula.
Right.
Yeah.
So then after he talks about the coefficient groups, the actual result we're after. Yeah, it's kind of weird. He tries to give like some natural way these homologies with different coefficient groups turn up in topology, but the example he gave actually was not that natural. It's like a vector space over the group or something. This is weird. But I guess it's useful for something, otherwise they wouldn't talk about it. So, with that in mind, theorem 9.33 for topological spaces x and y, there's a natural chain equivalence Need to chain homotopy, hence. You get this isomorphism. And that was on page 266.
Mhm.
Then we can extend that result with the Kunith theorem. I don't know if I'm pronouncing that right.
Sounds right to me.
Do you know any German, Daniel?
I know how to pronounce the German thing.
Ah.
Tag.
Is it mostly phonetic?
Ich verstehe nicht.
I think so.
I want to learn some German after I graduate, so I can read some of Gensen's original papers.
Mm.
So, well, I'll just get to the point because the rest of this is kind of technical,
you don't have time. You don't
tec-
have time to write it out.
technical,
No.
generalized, abstract nonsense.
Mhm.
So, part 2 says that this exact sequence splits, that is, Hn of...
So you got two pieces. The one piece is just the homology groups tensored with the homology groups of the group,
Right.
and then direct sum with the torsion piece that's formed from the homology of the chain complex paired with the homology of the group. And I assume that that pairing, well, where was that? Well, I guess I'd have to remember the torsion, how that was defined.
And there you go.
Yeah, torsion's always on a pair.
Although I guess...
Hmm.
Wait, that may not be... Okay, so the actual result we want, though, is this theorem...
Kunith
I
formula.
just wrote down the... I wanted theorem 3.7.
Oh,
That's the formula. Not this. This is still kind of...
Oh, you mean the
Besides the
Hn,
point.
the last, the right before proof, it says Hn of x cross y isomorphic to the sum.
Right.
And-
This is what we actually want.
Yeah, and that, of course, that sum is really a direct sum.
Right.
Another
right.
book you might see this written as big plus circle I plus j equals to n, hi sub x tensor with hjy.
Well, I think that's how they defined it.
Yeah, no, I'm just saying that his use of summation for direct summation is something he has recanted of in his later years. If you read
Oh, really?
more recent books.
He used like dots or you're saying he uses like
Big plus circle
gotcha.
I plus j equals to n there. Yeah,
Yeah.
that's it's what it means, but
Right. Yeah. I mean, I could write
that
this
sum
as,
is
like
is a very sneaky thing.
yeah.
What he means there.
This as like
Oh no. What have I done?
there, happy. Using functional programming notation. I'll write it normally here.
Well,
Actually, technically, that's not correct. I need to write more there to make it correct, but. There you go.
and that is the Kunith formula. And then the power of that formula is bared out in examples 9.13, 14, and 15, where he actually just cold calculates homologies of cross products.
Yeah, I'm not entirely sure how he does it with the wedges, though. I'm
Yeah,
not sure how that works.
I should look at this. I might need to revisit this when I talk about the cohomology. I don't know. It might be. I don't know. If we have time, we should try to work those examples out in here. I'm not sure when. I do think next time Daniel should start into the would say not next chapter, the homotopy groups, right? Yep. And then either I will have a day or two left for cohomology in our regular meeting, or I will invent additional meetings during the final exam week. So as our time permits. And then of course I have to find you guys a test. Just like a test, I'll give you guys a test. I'm sure I have some somewhere.